Okay, everyone, how you doing? Jim Malis again. Let's look at Chapter 8 a bit. We're eventually either in this particular video or in the video immediately following this one, we will do these problems. So it may take one or two videos to do it. I like to break up the videos a little bit. Sometimes the videos are quite long. I'm trying not to make them very, very long, but sometimes they get that way. So we'll figure it out. Regarding this stuff, these four problems from Chapter 8, 27, 49, from Chapter 8, problems 27, 49, 77, 84. Let's see what we can do, and within the next two videos, we'll get those done. Let's talk about Chapter 8 from the Katz book, Conservation of Energy. The whole idea of the concept of energy and various forms of energy that are out there. There's energy, it's a tough statement to kind of make. Motion means a whole lot. I mean, even when we're talking about thermal energy, it pertains to the motion of objects to a large degree. If there's a frictional force because you're pushing a very large object across a surface, as you push that object across the surface, there is a frictional force opposing the motion that you are generating. That frictional force will manifest itself in thermal energy. It'll get hot. The surfaces will get hotter. There'll be a transfer of energy. The frictional force associated with the work that you're doing is going to dissipate the work that you're doing. You're not going to be able to work as effectively. You're not going to be able to push it as fast or as far because of the frictional force. Because you're fighting the frictional force, thermal energy is generated. So you can kind of look at something like that in that regard. If I go and pick up an object of mass M, let's say it's mass M, it's 10 kilograms, let's say. I pick it up and then I walk up to the very top of a building that's 100 meters high. I have given the object, and my own body for that matter, but let's just talk about the object, let's ignore me. The object has been given potential energy. What do you mean? Well, if I take the object and throw it off the top of the building, it is going to land. We're going to ignore air resistance and everything. It is going to land and hit the ground very hard. It's going to hit it a lot harder than it would, no friction, no air resistance or anything like that here. I threw it from the top of a 100-meter tall building. Sure, it's going to hit the ground pretty hard. It's going to hit the ground a lot harder than it would if I threw it off a 10-meter high building or a 5-meter high building or even a 50-meter high building. The fact that it's 100 meters high, the higher you go, the more potential energy there is associated with it. Why is there more potential energy? Because you did a lot more work to get up there. The work that you did to get up there will be released in kinetic energy at the very bottom. There's a lot going on here, guys, so it's hard to kind of, let me, again, it's always the assumption we're reading the book, and I'm going to try to augment this as best I can, and we'll see how we can talk about this as much as we can. Regarding energy, let's talk about it. Let's see what we can say. There's frequently two kinds of energy that get spoken about. It's called potential energy and kinetic energy. Potential energy is energy that's stored, in a sense, and if you just flip the switch, so to speak, if I'm flipping the switch in the instance of me in the physics experiment throwing the 10 kilogram mass off of, or pushing the 10 kilogram mass off of the top of the 100 meter tall building, it had potential energy, and all that potential energy is going to be manifesting itself. It's going to keep losing potential energy. While it's losing its potential energy, it's gaining kinetic energy. At the very bottom, it's got no potential energy. All its energy is kinetic energy. So potential energy is energy stored, and you can set it into motion at some point. Kinetic energy is from the Greek word kinesis. Kinesis. Kinesis is motion. Kinetic energy is the energy of motion. The word energy itself has got kind of some, it's pretty fascinating in its own right. There is energy, N or G, energy, energia. in Greek it'd be this, just a little change in the ending. Ergos is work. En is in. Looks like in even. I mean, just replace the E by an I, you got in. So you can see the Indo-European origin of the word. It looks a lot like in. Okay, it should. I mean, they're the same language family. En is in. Ergos is work. Energy, inside of energy is the capability to do work. I don't know that that's a great definition of what energy is. I've read different places, not really a good definition of it, but we know that energy has the capability to do work. Inside of energy is the capability of doing work. Inside of it is work. Inside of it is the capability to do work. So that's what we mean when we talk about energy. Well, what's this thing called work? Well, we kind of talked earlier about force, and we said force was equal to mass times acceleration. Yeah, I guess that made some sense. We knew that the force that we're talking about is great if there is a great mass experiencing a great acceleration. If the mass and the acceleration are both very large, the product of the two is very large, it is indicative of a great force. If the mass under consideration is 1/10 the size of the first mass that we were talking about, but the same acceleration takes place, it's 1/10 the force. So in other words, if I said to you, well, let's take the mass and make it 1/10 the mass, and then multiply by acceleration. That's the same as, I mean, you could do this a bunch of ways. That's the same as just 1/10 right on the outside, and you got this guy right here. Well, didn't we say that guy was just force? This is 1/10 the force. If you take the mass and have it be 1/10 what the original mass was, but the same acceleration is taking place in both circumstances, if it's 1/10 the mass, the force that is required is 1/10 the force. It makes sense. The object's 1/10 is massive. For the same circumstances to occur, but 1/10 is massive of mass to be present, 1/10 the force should be occurring. What if you leave the mass as is and you make the acceleration 1/10 of what it was? Take that 1/10 out of there. I did not say it's the same circumstances, but the numbers grind out to be the same. And that's also 1/10 the force. 1/10 the original force. So on and so forth. So we kick this thing around. The amount of force experienced is directly proportional to the product of the mass and the acceleration. Makes sense to me. Great mass times great acceleration, very big number. The only way a very, very massive object is going to be accelerated very drastically is if a great force is applied. Sounds good to me. If a small mass is accelerated with a small acceleration, not a big number when you take the multiplication. Makes sense. Not a lot of force is required to do it. And that's where it's coming from. They do a lot of stuff. I don't want to get too cavalier about the whole explanation here, but there's a lot that they make up. There's a lot that they make up in science in their communication, and as long as they're consistent, they can draw some pretty fascinating conclusions. This is how they defined it. It really describes matters very, very well regarding force. Tell you what, how much work And I'll kind of jump ahead a little bit on this stuff, and I told you guys about the dot product and stuff like that as well. Well, how does work come into all this thing? Well, you do a lot of work if you exert a lot of force over a lot of distance. And you don't do a lot of work if you don't exert a lot of force and don't exert it over a lot of distance. It's kind of analogous to this guy. If M and A are both very big, F is going to be a big answer. If M and A are very big, F is going to be a big answer. If M and A are small, F is going to be small. Let's figure this out. Well, we got this thing called work. A lot of ways to talk about it. Let's be really generic at first, and we'll take it from there. Force times distance will give you work, at least for our purposes right now. Force times distance is equal to work. What does that mean? Well, I tell you what. Let's say I'm pushing an object, and I don't want to get overly specific here, but I do want to say a couple things. I'm pushing the object from here to here. I am pushing it a distance of distance d. I'm exerting a force F. Don't want to get overly specific right here, guys. Right now, let me just say that. Somehow, some way, I'm exerting a constant force F over a distance d. Perpendicular, or actually parallel to the motion. Work equals force times distance. Do you understand if you were to make the force that you were exerting 10 times greater, if you were to make the force 10 times greater, work is going to be 10 times greater. Everything else kept the same. Or if you just kept the force the same, but made distance 10 times greater, the work would be 10 times greater also. Let's talk about this. If you said, okay, this is what you said, Melis, now let's go here. Let's go 10 times the force. I'm really going to exert a great force over a distance d. I can pull the 10 out of there. That's FD. That's the original W. This is just 10 times. This is 10 times the work of what I did originally when I was working with that guy. Well, let's say I don't go 10 times the force, but I go 10 times the distance. Pull the 10 out of there. Doesn't really matter. By one way or another, it just happens to be the same thing. 10 times the work. That's an easy scenario. Well, let's keep talking a little bit, you guys. Let's keep talking. If see what we can say here. Let's say somehow, some way here, you are. There's a lot of ways to do this actually, but let me take that force F right here. This is theta. This is F. This is, I don't know how to, forgive me guys, I trying to kind of debate here how to go with this whole process. If this thing is F, this is F sub Y, this is F sub X. You always look to do the multiplication with things that are parallel to one another when you're trying to find out what work is. When you're talking about work, you're putting everybody in the same line. If they're not in the same line, you got to bring them into the same line. The work would be F sub X times D. True, but F sub X is F cosine theta. F cosine theta. A lot to be said here, guys. I don't want to give too much more detail than maybe would be useful. You got this right here. What is going on? Yeah. You've got to make it so the guys are all, the force and the distance are in line with one another. If they're not in line with one another, make them in line with one another. Make them in line with one another. Okay, so what? Big deal. Well, W is a scalar, force is a vector, displacement's a vector, and that's equal to the magnitude of F times the magnitude of D times the cosine of the angle between them. Wait a minute. F times D times cosine theta. Is that true? F times D times cosine theta. F times D times the cosine of theta is the same as that. This is the cross product, this is the dot product that we talked about some time ago, so to speak. This is the dot product I've already told you about. When I talked about the dot product and the cross product, and we talked about a bunch of stuff, right? Let me leave it like that. There's more detail. What am I saying? More detail. What do we mean? You could say that is f sub x d sub x, f sub y d sub y, f sub z d sub z. Well, we're not really going into we're not going in three-dimensional space. We're not y doesn't play a role in this. There is no this guy's got no displacement. There's no displacement here in the y direction, nor in the z direction. It's just this guy. And this guy would solve it. But technically, you'd go down to here if you wanted to, if things were generally spoken. Okay? So that's the deal. That's the deal in something like that. This is kind of interesting in the sense that, give me 1 second here, guys. If this is kind of the rigorous way to write it, this is the rigorous way to write it. And that kind of, we can interpret that as f d cosine theta. What's going on here? How much work would get done, guys, if you made theta really big? Not really big. How about 90 degrees? If you open it up like this, it went straight down that way. If you opened up theta to 90 degrees, what's the cosine of 90 degrees? It's 0. If I'm pressing straight down, and motion is occurring perpendicular to my straight down push, let's say you were somehow pushing straight down right here, and somehow this thing was moving that way. Or if you were pulling straight up, picking this thing up, you were picking this thing up and moving that way. The cosine of 90 degrees is 0. What does that mean? Let's say I was strong enough to pick up a weight that was, 200 kilograms. That's about 2,000 newtons. I picked it up. Now I'll start walking with it. In fact, I'll walk 1 whole kilometer. I'll walk 1,000 meters with that 2,000 Newton weight. Well, if I could do that, that'd be something else, wouldn't it? That's some kind of world record. Anybody who can do that, I guess, right? I can't do that. But let's say somebody could. Have they done work? In the mechanical sense, no, believe it or not. If you pick something up, you're exerting a force. Let's go over here. You're exerting a force of 2,000 newtons to pick the thing up, and then you're walking this way. Yeah, that's counterintuitive. If you could pick that weight up, all 2,000 newtons of it, if you picked up that 2,000 newton weight, if you picked up that 200 kilogram mass on Earth, with Earth having the G associated with 9.81 meters per second, if you pick that up, it's roughly 2,000 newtons. If you exerted 2,000 newtons straight up, the only work you did was picking it up 1 meter. It was on the ground. And you picked it up. You moved it 1 meter. That is work. Because you were fighting the force of gravity, and you moved the weight through 1 meter fighting the force of gravity. You did work there. Absolutely you did. Once you got it up to here, if you could start walking for 1,000 meters, you're exerting a force upward, and you're technically not exerting a force that way, the distance you're walking. Now, we all know there's a lot going on. The biochemical aspect of what's going on in your body, that's another story. There's energy being used for you to be able to be strong enough to pick that thing up and take a walk with it. There's energy being burned. I get that. There's chemical processes going on with the nutrition that you have, where energy, where energy is being retrieved, where it's being accessed. You are accessing energy to be able to do that job. I'm not going to call it work. That job. So there's energy that has to be accessed. Energy is being used to do that. But in the mechanical sense, it's not work. Period. Now, if you climb the stairs with that thing, it's another story. That's another story. I mean, if you do that, I gotta, there's a force of gravity pulling down that weight, 2,000 newtons. I'm climbing the stairs, exerting 2,000 newtons of force to just go at a constant speed up the stairs, and I'm going 100 meters. I got to overcome the weight of the object. To do that, I got to exert that force over that distance. Work equals force F dot D, we said, right? That's F D cosine theta. What's the angle theta between them? The angle theta between them is 0. They're right on. I mean, I drove them over to the side. I walked it over to the side here so you wouldn't have to, so you at least see it, but it's 0. The cosine of 0 degrees, ladies and gentlemen, is 1. It's just force times distance. Yeah, it's a different ball game. If I'm going to climb really high, you guys, basically, I exerted 2,000 newtons of force for 100 meters, going straight up. That's pretty crazy. 2,000 newtons times 100 is 200,000 newtons times meters. They call those joules. If you exert 1 newton of force, through a distance parallel. These are parallel to one another. If the displacement and the force work parallel to one another, 1 Newton of force exerted over 1 meter, 1 Newton of force exerted over 1 meter is called 1 joule of work. If it's thousands of joules, it's kilojoules, millions of joules, megajoules, etc., etc. That's a lot of work to pick up that much weight and walk straight up. You don't eat. Now you're saying, well, wait a minute. How come I could be going sideways. Look, stairs are made in such a way. You usually don't climb stairs straight up like you're climbing a ladder. Why is that? Because it'd be too difficult to do, generally speaking, for a lot of reasons. However, it does not matter how you get up to a certain height. You might say, what are you talking about? I mean, if I'm going to climb to the very, very height of a very, very tall building, the very great height, and somebody put a ramp that was very long, the ramp could almost seem like it's level ground when I climb. I mean, it's not level ground. It's never level ground. But if the ramp is put in such a way, I could probably push my car up to the top of that building if there was a really, really long ramp from UWM to, the EMS building. On top of the EMS building, the ramp starts, and it goes down all the way down to North Avenue. Well, that ramp is not really a very strict, a very drastic ramp, a very drastic incline. I could probably push my car up there just as easy as pushing it on the ground. Perhaps. What's going on then? Well, there's not a lot of work. Sure it is. You're walking a very long distance. That ramp might be from here at UWM to North Avenue, or it might be from UWM all the way down to downtown to Wisconsin Avenue. It'll be easier for you to move something, but you'll have to walk a very great distance doing it. The force you will exert to push this cart up the hill is probably not very much at all, but you got to do it for a great distance. Whereas if you somehow were really, really strong, you're like Superman or something, or Wonder Woman or something, or whatever, some superhero, and you could tie 2,000 pounds onto your back, and then the ladder was strong enough, you just climb straight up. Wow, you're not having to take that long walk like you took from Wisconsin Avenue all the way to UWM. Here you're just going 100 meters straight up. Yeah, your walk is much, much less. I don't know how much less. Yeah, it's hard to put a number on it. Maybe 1,000 times less or something. I don't know. 100 times less, 1,000 times less, whatever. 100 times less is the distance. Right. You're going to get away with going 100 times. You're going to get away with going 1/100th the distance, but you got to pay for it. You're going straight up. You're going to have to lift 100 times more weight. You're lifting the same weight. You're going to have to exert 100 times more force to make the lift. That's why people use ramps. That's why they use inclined planes. It's easier to just pick something up 2 meters and put it there. Yeah, but if it's so massive, it's better to have a ramp that's 20 meters long. That's 10 meters long and just walk up that way. If the ramp is strong enough, you can get up there easier. So I'll make a long story short. It doesn't matter what kind of staircase you got over in the EMS building, or if you got a ladder on the outside of the EMS building. If you climb all the way to the top, the work you do to go that way, or just going this way, just going, taking the flight of stairs, and those flights of stairs are ramps. They're kind of like ramps. They make it a little easier to climb. Sure, they make it easier to climb, but you are proportionally walking a greater distance. Okay, so that's some of what's going on there. They call it a conservative force that you're dealing with. Gravity is a conservative force field. It doesn't matter which way and how I get up to the top of a building. Whether it's a very long ramp that barely slopes upward because the ramp is so long, or whether I just climb a ladder straight up. The force, the force field itself, fighting that force field one way or going up the stairs, which go like this, like this, like this. Doesn't matter if you're going over a ramp that's like that, to get to the top of the building, or whether you're going by stairs that are doing this to do it, or if you're just going straight up. This one requires the least force on average, but the greatest distance. This will require a little bit less force, but you still got to go a decent distance. Here, you ain't going that far regarding distance, but you need a lot of force. One way or the other. The work in all instances is W, it's W, it's W. The work it's the same amount of work in all instances. Gravity is a conservative force field. Gravity is a force field that no matter how you overcome it to get somewhere, fighting that force field, no matter how you fight that force field to get to where you want to go, no matter what path you take, the amount of work that you do is the same in all instances. Whether it's the ramp or the zigzag or straight up, it's a conservative force field. Friction's a non-conservative force in the sense that you do work to overcome friction, but once you stop doing it, the friction doesn't like shoot the crate back at you, sending it back to the place where you started. It's a non-conservative force. It's a non-conservative force. Whereas gravity's different. If I pick it up all the way to the top of the building and I let it go, it'll come right back down. Whereas with friction, it doesn't happen that way. You push something, you stop, it's not going to, bam, go flying the other way. Okay? So that's some of what's going on here, you guys. Let's take a look at a few things. Let's say a couple things and see how we can work with some of the problems. I think the problems, like I said, you know, those of you who have dealt with me, maybe not many at this point, I mean, given the health crisis we're dealing with, but people who have dealt with me person to person knows that the problems contain so much of the information that we want. If we can do the problems, we know what we're doing. If we can explain the physics within the context of the problems that we are encountering, I think we're doing pretty good in that regard. Okay. The problems being solved is like a picture being worth 1,000 words, as that old saying goes, right? Within the context of solving the problem, we can talk about a lot of what's happening with the physics. Well, before we get there, let's still talk about the physics straight out in the lecture type format that I'm doing right here for chapter 8. And then we'll get to these problems soon, probably more than likely the next video rather than this video. All right, what are we going to do? Well, we're going to do a lot. I mean, we can say a bunch of things, guys, related to this stuff, I think. Try to figure out some of the stuff we talk about with the potential energy and the kinetic energy and stuff. Give an example. Let's say one way or the other, I will fight gravity and I'll get to a height h or to a height d or whatever you want. D is equal to h. Let's say h is the height. This is close to the surface of the Earth, so we're not going to talk about some rather interesting stuff that can happen. I mean, in other words, how the constant g, the gravitational field is given by g, believe it or not. The 9.81 meters per second per second. That gravitational constant is only a constant near the surface of the Earth. The further away we go from Earth, g gets smaller, and we've gone into that. We've already talked about that kind of stuff. So, if you want to see here, let's just keep this as is. Picked up the mass m, and moved it here, fighting gravity the whole time, and I got it up to here. How much work have I done? Well, they're parallel to each other. So we know this. And we know that. We know that they are parallel to one another, so the angle theta between them is 0. And we know that you are overcoming a force. You're doing this at a constant speed. If you did this with much greater speed, if you did this with much greater, if you were like accelerating while you were doing this, greatly. I mean, there's a lot can be said here, guys. I'm kind of sort of throwing a few things right by you in the interest of at least getting the basics under control here, and we'll do things as we need to do them, I guess. First things first. I'm going to bring this thing up relatively slowly. It's nothing really drastic, but I am overcoming gravity. I'm overcoming gravity with a force of mg. How's that? The weight of the object, the mass m, has a weight mg in the gravitational field g. Mg is the weight that I have to overcome. I will pick up the weight and work against it. I will exert a force mg and somewhat slowly bring it all the way to the top to h. The force is mg. The distance I traveled is h. Work that I did to get up there is mgh. Work that I did to get up there is mgh. So, yeah. Well, that work mgh, when you stand up, when you have that thing up there and you leave it on the ledge, there's nobody down below, there's just a sand pit, and you're just experimenting how fast the thing goes, how much everything, how things work out and stuff, right? W, let's see what we got here. W equals mgh, so they call that, the work I did to get up there is mgh. I gave that mass potential energy mgh. I gave that mass potential energy. If I let it go, at the very bottom, it's got no potential energy. I got it, potential energy is kind of an arbitrary thing, you guys. You can kind of assign random numbers to it, but once you do, you got to be consistent. In other words, I could say right now, my potential energy is, I should say it's 0 because I'm not anticipating that it's some game show and I'm going to fall through the floor or something. But I mean, I'm just standing here. This is potential energy 0. And if I go to the 4th floor, it's potential energy mgh, which is my mass times g times the fact that I climbed 30 meters to get up there. Okay? So that's the potential energy. If you drop this mass from that h-high building, that building which is h-high, at the very bottom, all its energy is going to be kinetic energy. Very, 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 very oftentimes, all of the potential energy and all of the kinetic energy of a system, kinetic energy is energy of motion. We're going to get into that in a second. All of the potential energy of a system and all of the kinetic energy of a system equal a constant for a given system. Well, hey, look, never say never, never say never, never say always, a friend of mine said one time. He's right. But for our purposes, in a particular closed system, the kinetic energy and potential energy, when you add them together, is a constant. What the heck does that mean? And I got another question. How big's the constant? Well, I could write that in a lot of ways too. The constant is mgh. They always add up to mgh. What does that mean? That means right up here, mgh is that constant. If you push that mass off the building, when the mass gets over here, it has potential energy. It still has potential energy. It still's got height. It's only got half the height though. If it's got half the height, it's got half the potential energy. Great. I just said if I add kinetic and potential, it's a constant. Up here, there is no kinetic energy. From the Greek word kinesis, motion. There is no motion energy up there because it ain't moving. There's got to be a velocity, and there ain't one. MGH is the potential energy up here. The kinetic energy up here is 0. MGH plus 0 is MGH. That's everybody. Down here, while it's falling, what's going on? Here, ladies and gentlemen, there is a kinetic energy. It's got motion energy, and it's got potential energy. And when you add them together, it's the same constant. This guy. Numerically speaking, it'll add up to that. At the very bottom, right before it hits the ground, what is going on? We just said it's the same amount of potential energy. It's the same amount of energy, the total energy, which happens to be what the grand total potential energy was way on top. Down here, there's no potential energy. Got to remember, up here, potential energy was a max, and kinetic energy was a min. Here was kind of right in the middle. Here, kinetic energy is a max, potential energy is 0, is a min. Potential energy is 0 down here. Not this guy. Let me get that guy out of there. Down here. Potential energy is a min. It's 0 down. There's no potential energy. There's no stored energy right here. Everything uncorked, and it's all kinetic energy out down at the bottom. Here the kinetic energy is 0. It's a min. And the potential energy is a max. Here, the kinetic energy is a max, and the potential energy is 0. Anywhere in the fall down here, as this falls down, anywhere in the fall down, the potential energy and kinetic energy are going to equal forgive me here, guys. The potential energy and kinetic energy are going to equal a constant. Tell you what I'm going to do. The initial potential energy, way on top, was MGH. The initial, and there was no kinetic energy, right? So there was no kinetic energy. So you could basically, there's a lot of ways to write this, guys. Let me kind of go there. Let me I'll make sure some of this stuff is legible, guys, when we do it. All right. Initially, ladies and gentlemen, there is no potential energy way on top. It's all, I'm sorry. Initially, okay, start that one over, guys. I mean, I didn't say that the way I wanted to say it. There is potential energy initially present in the system. There is kinetic energy initially present in the system. It might be 0, but I got to call it something. And in the end, there is a final potential energy, and there's a final kinetic energy. We just said, when I said it's constant, I mean it's constant. Whoever's the beginning and whoever's the end, it doesn't matter. PEI plus KEI equals PEF plus KEF. So what do we got? We got MGH in the very beginning, and it ain't moving, so the kinetic energy is 0. At the bottom, it's at the very bottom, so the height is equal not to h, the height's equal to 0, so it's mg times 0. Well, that's just 0. That's just 0. And I'm going to get into this in a second. Let me write that, but I'll derive it for you later. It's not that bad. It's kind of an interesting look at it. The kinetic energy, the energy of motion, is 1/2 mv squared. If that's the case, I guess there's a lot of math we could do here. If you looked at this, right here and you wrote it like this, say, hey, look, Malus, I'm going to find out how fast that thing's going at the very bottom, if you don't mind. The m don't matter. Divide by m on each side. Divide by m on each side. Divide by m on each side and multiply by 2. Now square root both sides. I haven't told you where we got this yet. I'm about to. Look what I just did. Look what I just got. I do believe it. Based on things that we've already done, you guys. Based on things that we've already done. Forgive me, guys. I'm trying to find the best chalk here that's going to work for this. Some of this. You've been teaching as long as I have for more than 30 years. You become like a connoisseur of chalk, I guess. What works best, I think, right? Sometimes I find the good stuff. Sometimes I don't. All right. Look at that answer. I told you that I believe it. I think you're going to believe it too. Do we remember F is the final. You know, you can say the final speed at the very bottom too. That's not a real big deal. Put an F here. I'm not looking to split hairs with people. I'm saying what's the speed at the very bottom? The speed at the very top was what? VF is the speed at the very bottom, and we said it's the square root of the product, 2GH. But the speed at the very top was VI. And VI was 0. I just pushed it off the ledge. Initially, it wasn't going fast at all. Do you guys remember this? Yeah. Everybody's falling down, so we're going to call down positive. It's going to fall down a distance. D, and that distance D we're going to call h. VF squared is the speed at the bottom. VI squared is initially when it got pushed off. That's 0. The acceleration due to gravity is A. That's the acceleration due to gravity. It's falling straight down. I want you to look very, very carefully. I want you to multiply by 2GH on each side. VF squared minus 0 squared is VF squared. Square root both sides. VF equals the square root of 2GH. VF equals the square root of 2GH. It works. Through energy considerations, I was able to derive what VF is equal to. Through all this song and dance, we got down to here. Through energy considerations. We did all of this, got to here. Also, through the kinematics, you're getting the same answer. Guys, that's very, very important. Not only is it very important, it better happen. I guess it means the same. It's very important because it has to happen. You can't be making up the mathematics as we go along. You can't be making up the physics as we go along and have the physics not agree with itself. The physics has to agree. If I'm going to build a bridge that works, if I'm going to build a car that works, if I'm going to build an airplane that flies, the physics better be working. The physics better be spot on. And the kinematic equations the kinematics confirm what we found through energy considerations. Yeah, I know I haven't talked about him yet though. So let's do it. What is a general statement for kinetic energy? How do we do something like that regarding kinetic energy? Okay. It all works. It all works if you believe this. If you believe that kinetic energy is 1/2 mv squared. I'll talk to you about it. Tell you what. Let's make it pretty easy, but let's hopefully very believable as well. Okay, let me clean this up a little bit, guys. Some of this stuff erases better than other stuff. Let me just see what's going on here. All right, guys, what's going on here? Where did this thing come from? Where is this kinetic energy coming out to be this? Sometimes they say delta KE, change in kinetic energy, is 1/2 mass VF squared minus 1/2 mass VI squared. So on and so forth. 1/2 mass VF squared minus 1/2 mass VI squared delta K, change in kinetic energy. You got to remember, something might have started going really slow and it got more kinetic energy with the passage of time because an acceleration was taking place. How does anything slow down? How does anything speed up? Nothing slows down nor speeds up unless there's an acceleration present, an unbalanced force present. Something will accelerate if it's already moving or standing still or perhaps going in one direction. You change. There's not going to be any kind of acceleration unless there's an unbalanced force happening. You will have a change in kinetic energy if an acceleration takes place. If an acceleration takes place, you're changing velocity. If you're changing velocity, you are changing. Well, there's a lot going on here. But essentially, an acceleration taking place vis-a-vis, let's for sure say vis-a-vis straight line motion. If there's an acceleration that is taking place, there's going to be a change in kinetic energy if the change is taking place along a straight line. There's other things to talk about. Let's not talk about that now. Right now, let's say if something's traveling in a straight line and you're going to speed it up or slow it down or whatever's going to happen, if there's an acceleration taking place associated with straight line motion, there's going to be a change in kinetic energy. Okay, great. All right, I've already more or less delivered this speech. I certainly threw this at you, but I didn't tell you why it's true. Is it true that if something's going on in a straight line, let's not worry about any angles right now, guys. Let's not worry about any angles. Is it true that force times the angle between them is 0? It's FD cosine theta. That's what work is. FD cosine theta. If theta is 0, the cosine of 0 is 1. That's FD. W equals FD. W equals FD. Well, okay, great. That's the work that was done. If the work done is force times distance, would you allow me to say that force times distance is work? Is force associated with a mass being accelerated? There is essentially for us, at least especially in regard to straight line motion right now, and I can do a lot of stuff. Even if it's not in a straight line, if things are going in different directions, I can mimic things to look like straight line motion for small increments of distance and from small increments of time. Okay. I'm not going to get too much. Let's not get too far into this. Let's just say mass times acceleration. If you put an acceleration onto a mass, you are doing so because you're exerting an unbalanced force upon it. And if you move it through a distance d, you have done work W. Force times d is work W, and we got this right here. Is it true? I already kind of erased it, but is it true that acceleration let me try to figure out how I want to say this. Do you guys remember that we said that acceleration is VF minus VI over T? Correct? I just want to argue with this a little bit for a second, guys. I want to kind of think of a few things to look at here. That is true. That's definitely true. We also said that D is equal to VF squared minus VI squared over 2A. Yeah, we've said that. We've done this. We've done that. You just saw me talk about this in the kinematics, repeating some of the kinematic equations and the arguments associated with the kinematic equations earlier, just now, last 5 minutes, 10 minutes, whatever. You saw me do it. Let me see. Yeah, I guess you could say that's true. You can say that indeed is true. Distance is that, acceleration is that. I think I'm going to stay like this. I don't really have to go here, but I really need this. I can go here if I want. I'm choosing not to. I could, but I'm not. I'm going to call this guy the acceleration. And I'm going to say D all right, time out. Time out. What's going on here? This right here is what D is, given the acceleration that's going on. This is A. That cancels. That cancels. W equals The work you did is the change in potential, the change in kinetic energy. Change in potential energy will give you the same answer. Oftentimes. There's more to this than meets the eye, you guys. The work right here is equal to the change in kinetic energy. Delta KE is the work that was done. Delta KE is 1/2 m Vf squared minus Vi squared delta KE yeah. What if the thing started from zero? What if the thing started with zero velocity, or the magnitude of velocity was zero? Then it's just this, 1/2 m Vf squared. So generically, I guess you could say, or generally speaking, they write Ke is 1/2 Ke is 1/2 mv squared. K equals 1/2 mv squared. That's definitely of interest. So that's where kinetic energy is coming from. That's what they're saying, something like this, you guys, vis-a-vis kinetic energy. So let's talk about some more stuff, guys, regarding this. They're saying, okay, how does this stuff work with gravitational fields and things of that nature? And I think when we do this, there's some other stuff I'd like to actually say. So I guess you can store up energy by climbing up to the top of the building and pushing the weight off the top of the building. You store up the energy by climbing up to the top of a building and then pushing the weight off the top of the building into the sandpit below when we're doing our physics experiment. So climbing the building, you're storing up energy at the very top. That's a lot of potential energy, and you can convert it to kinetic energy. If you take an ideal spring and stretch it or compress it. Now remember, an ideal spring stretches with the exact same difficulty as it compresses. Compressing an ideal spring by X meters or stretching an ideal spring by X meters is the same amount of difficulty. Each one of those processes stores up energy. If you do work on the spring and stretch it or compress it, you have stored up potential energy. So if you let the spring go, like in a dart gun or something like that, if you turn the spring loose, what happens? All that potential energy goes into kinetic energy. 1/2 mv squared. So let's talk about it. Let's say a few things to have this thing sort of, pretty much there for us, and then we'll take it from there. Okay, so let's see a couple things here, guys. Forgive me, I got to clean this up a little bit. All right, guys, we'll fix that a little bit down the road, I guess. Let's see what we can say. Well, we talk about the spring, right? The ideal spring. Here it is. This is at x equals 0, and you got a delta x on there. So this is somehow x equals 0, no kind of stretch. And here's some kind of stretch, here's some kind of compression, or here's some kind of stretch. It can go one or the other on that. Didn't we say that? Let's say this all happens perpendicular. They all happen in line with one another. So the angle, you know, when we say this, we'll say that's coming out to FD cosine theta. We'll say that they are perfectly parallel to one another. So it's coming out to this. Well, you can't really, it's hard to do that. I mean, yeah, this is, no, there's no I can't on this one. We can do it. This is what we're going to do. But you got to be careful. The force, in terms of magnitude, is kx. It's actually negative kx. We're not going to go there. Right now, we just care about the magnitude. I already know what direction this thing is going. I am going to compress this thing. I'm going to compress this thing, or I'm going to stretch this thing by x units either way. It's the same amount of work that's done. Do you understand the amount of force that you are encountering depends upon how far you are in the compression? How far are you compressing this thing? The more you have compressed this thing, the more fight the spring gives you if it's an ideal spring. The harder it is for you to hold it in place. So there's more force required as you move around. Well, if we're going to, you know, for 209, for the physics 209 that I'm teaching, if it's a calc-based approach to this thing, you're going to basically say that the work is going to be an integral from x1, you know, from x sub I to x sub f, whatever. It's going to be f dot dr or f dot dx. Let's just say fx right now. What's going on here? What it means is the work is the integral from where you, now we said we start at x sub 0, we'll just say is 0 in this case. In this case, we started the thing was not compressed. Doesn't have to be. You could be in a place where it's already compressed somewhat, and you're going to compress it even further. Or you could be in a place where you've stretched it a little bit, and you're going to stretch it even further. This is 0. This is x sub f. Integrate integrate kx dx, and it comes out to 1/2 kx squared for the potential energy. It's the amount of work. This is the amount of work that you got to do to compress it x units. To compress it x units. And there's a lot of ways here, guys. I don't, you could say that x sub f is whatever it is, x sub I is whatever it is. Let's make x sub f just equal to x. And when you do it, you got it from 0 to x. The work that you did starting from 0, compressing it x units or stretching it x units is this. So that's another component. That's the work that you did. That's also an amount of potential energy. If you leave it there, leave it in waiting to be actualized, to be used, to be actualized as kinetic energy, that's it's in waiting at that point as well. It's 1/2 kx squared. So essentially, in a lot of the work that we're doing, you guys, and we'll get more into this as time proceeds. I mean, it's a little essentially, guys, I mean, what I always show people in practically all of these systems, even in chapter 9, when they get into looking at things another way, the energy initially under consideration, all energy associated, all the energy that's initially present, or much better put, all the mechanical energy, things that we've been dealing with throughout this discussion right now, all of the mechanical energy, initially present equals all of the kinetic energy finally present. The initial presence, the initial accounting of all the mechanical energy is equal to the final accounting of all the mechanical energy. Initial mechanical energy of the system equals final mechanical energy of the system. So if you got potential energy, initial, kinetic energy, potential energy initial, kinetic energy initial equals potential energy final, kinetic energy final. Yeah, and there might be other energy considerations that come in here. What got dissipated in friction? I could figure that out too. I could say that what was all initially present finished up here plus work that is non-conservative. Could be right here. Oh, all of this that was initially present went here, and it went to friction. And friction I can't really get back, but I got to account for the fact that things got heated up. All that heat that happened as a result of the work that I was doing, I'll account for it. Essentially, guys, you're always coming back to here. This is always going to work. Later on, you're going to see this thing called momentum, mass times velocity. The momentum of the universe is conserved. The energy of the universe is conserved. Now, if you want to call energy, they say mass and energy have a close association. You can convert mass into energy, and I believe there's a lot that goes on, guys. I don't want to talk and claim to know what people much more knowledgeable than I know. But the energy of the universe is conserved. Let's leave it at that. Energy of the universe is conserved, and momentum of the universe is conserved as well. But right now we're dealing with energies. We're not going to worry about that. We got to here, that WNC, that's non-conservative. The WNC would have been the non-conservative work that you had done there, okay? I'm not putting that on there now. We'll see that. We'll account for that some other time. So let's say there was something like this. 1/2 KXI squared plus, whatever's going on here. MG XI here plus 1/2 MVI squared equals 1/2 KXF squared plus 1/2 MGXF plus 1/2 VF squared. Basically, you got to just do some bookkeeping, guys. What does this mean exactly? I don't know. This thing could be, there could be a lot going on. This thing could be a spring that's standing on end. And, the X is how far you compressed it and what height it is. There's things I can do here. Don't take this, I don't want to, you don't want to tell people don't take this too seriously, but if you have it set up in such a way, you could say, for how this system's conducting itself, there could be, let's say, let me say something different to kind of get myself a little bit out of the woods, because this could be, I want to say it, there's a lot of ways this can be said. So let me at least let me be a little more, how would you say this? Let me be a little more generic, I guess you could say. Look, add all the potential energy on one side, with the kinetic energy on the other side, add all the potential energies, add all the initial potential energies together to get the grand total potential energy. The grand total potential energy plus the grand total kinetic energies, the grand total potential energy initially present and the grand total kinetic energy initially present, add them together, that equals the grand total potential energies finally present plus the grand total kinetic energies finally present. Guys, the big thing is here. The big takeaway is that one right there, and the real big takeaway is that one right here. Okay? So, let's talk about this. They say a few things regarding orbital motion, circular motion. This integral is rather interesting. You do the integral, it gets you to here. It's kind of neat. You could have taken, on the big side, the force, if you compress something x is the max, kx is a big force. Initially, you started at x equals 0. If x equals 0, what's 0? If x equals 0 initially, what's 0 times k? It's 0. If x now is the max, and we'll just call it x, it's kx. What's kx plus 0? It's kx. Average 0 plus kx, you get 1/2 kx. If you were to take the big one, kx, plus the small one, average the two, then multiply, this is the average force. Then take the average force and multiply by the displacement. Didn't we say force times distance would give you work? Didn't we say work was going to be force times distance? Can't we say that, hey man, the high end of the force that you got to fight is kx. The low end is 0. You started out, k times 0 is 0, and k times x is the big one. You got this right here. You got this times x. Kx plus 0 is kx, divided by 2 is 1/2 kx. That's the average force. Times the distance, force times distance. For those without a calculus background that are watching this, that's another way you can do it. For the 209, you do the integral. And the integral is going to be pretty interesting stuff when we deal with it. Okay. Let's talk a bit. All right. Forgive me, guys. I got to make sure I got... It's a throw of the dice, which chalk is good. Some of it's pretty old. Okay. So we have what we have. We will get to that probably the next video. And in the meantime, let's see what we can say here. There's a few interesting things that they say. I'm going to remind you to look at integrals. So let's see what I can say. And the book's got some great examples, you guys. The non-calc book from the publisher and the calc book from the publisher as well. We are, again, this is formally Physics 209, so it's calc-based, okay? So you got to kind of, but the book, Chapter 8, again, be reading it. They do a great job. I kind of sort of said that potential energy is kind of an arbitrary thing. Yeah, I guess you'd say yes and no on that one. I mean, I could say I'm standing right here and I said my potential energy, my gravitational potential energy is 0. Yeah, I guess I could say that. I could also say, and I'm not saying you should say this, but I could say my gravitational potential energy right here is 1,000 joules. Really, what are you talking about? Yeah, when I climb the building, it's 1,000 joules plus 10,000 joules. What's the change in my potential energy? It's 10,000 joules. If I started at 0 and went up, it was 10,000 joules. It's still a 10,000 joule change. The big thing with potential energy, guys, is it's a bookkeeping method. Now, I don't want to take that argument too far, and I know I just said, hey, I could say I'm 1,000,000 joules right here. Well, yeah, I guess you could say a lot of stuff as long as you're consistent. It's kind of like me saying, yeah, I can also say that I'm a millionaire as long as my categorization of that is not having a lot of money, I guess, right? And then, but I'm saying, well, then if I'm a millionaire, if I just gain $10,000, I'm a millionaire plus $10,000. Yeah, that'll work. How much money did I gain? Well, I gained $1 million. I gained $1 million plus 10,000 minus $1 million. Oh, $10,000. As long as I can get a difference there, they let you get away with a lot. I don't want to take that argument too far. I just want to say there's a lot of arbitrary stuff that does go on, that's allowed to go on, as long as things are consistent and as long as you can formulate a difference. Okay. Let's talk. Well, they've got this idea on our page in the Katz book, for Physics 209, the Katz book. There is page 221 talks about universal gravitational potential energy. Universal gravitational potential energy, how that plays out. They are essentially saying we're not gonna, how you can look at this and how all the twists and turns that we can take. There's a lot of them. My goal right now is let's have a real basic feel for what's happening here, and we can get, further progress, I guess, can be built upon the foundation that we build. Right now, let's build the foundation, okay? So what we're looking at, they're claiming the change in potential energy, change in gravitational potential energy. They write it with a U. They put a U there for gravitation. The U is the PE gravitational. You put a G right here for gravitational. I don't know. It's kind of an arbitrary thing. But the change in gravitational potential energy is called delta U. And they're saying it's this. Big M is the planet. Small m is the satellite or the rocket ship. Ri is the initial location. Rf is the final location in terms of distance away. And they write it, and they put a minus sign right here, and they say that's what it is. What is going on here? What is going on here? What's going on here and what's not going on here, I guess the questions that can get asked. And we're not gonna, we're not gonna, like I said, there's a lot of ways we can go here, and I just kind of put the brakes on the whole thing. I'm saying this is the Earth, or this is the sun, or this is some planet in some other galaxy, and this is Ri, and all the way to here, that's RF. So here's Ri, here's RF, here's the planet or the rocket ship, and this is the sun or the Earth or something a lot bigger. We're going to put them both, they're all both in line with one another. I don't want to get too crazy with this. We could, but we don't need to. We don't need to. We're looking at where they are. There's a lot can be said here, guys. Let me try to figure out how we want to say it. It's basically, it works with circles. I just said I don't want to go there, and I'm about to go there, but if you put this guy on a circle, you put this guy in a circle, it doesn't matter where he is on the circle. It doesn't matter where he is on the circle. Give me the difference between the two radii. Not the difference in locations necessarily. Not the difference in locations necessarily, but the difference of the two radii of the circles. If there's some grand circle, I don't want to draw it because I think I could have caused more harm than good, but if there's a circle this way, right here, circle this way, and there's a circle this way. One's of radius R1 and the one's of radius Ri and the other one's of radius RF. The difference of the two radii tells you the difference in location. Can I ask you a couple questions before we actually derive what I just did right here? G is a constant. M is the mass of the black hole, or the mass of the white dwarf, or the mass of the sun, or the mass of the Earth, whatever it may happen to be. And small m, so big M is any of those that I just said. Big M is any of those that I just said. And small m is the, small m could be the mass of the small, one of the moons of that planet. Big M could be the planet, could be the Earth, could be the sun, could be a white dwarf, could be a neutron star, could be a black hole. That's big M. This one right here is a satellite somehow, the moon or a rocket or something like some kind of rocket or something like that. Can I ask you a question here? G, big M, small m. G, big M, small m. Say it again. G, big M, small, G, and then big M, and then small m, same thing right here. Which one's going to be a bigger number? This mathematical operation carried out, or this mathematical operation carried out? The tops are the same. Don't worry about this. We're not sweating this just yet. I'm not worried about that. We're going to see why that's there, but not now. Right now, that guy right there and that guy right there. Which one's a bigger answer? If these are the same on top, the smaller the denominator, the bigger the answer. The smaller the denominator, the bigger the answer. Small denominator means big answer. Big denominator means small answer. When you subtract these, you get a positive number. Let me ask you a question. If I went from Ri, let's just say they're right in line with each other. If I went from Ri to RF, I am picking it up, fighting the gravitational force of this very massive object, big M. I'm fighting the gravitational force and pushing it up to here. The way I was pushing the weight up to the top of the building, the engineering and mathematical sciences building. The way I was pushing the weight, carrying the weight up to the top of the building. I was like loading up the gravitational spring. Not the 1/2 kx squared, but the mgh. 1/2 kx squared and mgh are both potential energy. For me to fight from here to here, what did I do? For me to fight from here all the way to there, what did I do? I gave the small mass, small m, I gave it an increase in potential energy. I gave it potential energy. I increased its potential energy. Are you telling me take this, divide it by small, take this, divide it by a small number, Ri, get a big answer. Take this, divided by, take this, divided by, take all this, divided by a small denominator, get a big answer. Take this, divided by a big denominator, get a small answer. The difference is positive. Yeah, I did a positive amount of work to get over there. Delta U is a positive answer in this case, and I end up getting this for an answer. What happens if you went the other way? You'd have to reverse. You'd have to put the RF right here and the Ri over there. It'd be negative. You lost potential energy. Okay. Now let's see what we can say, guys. Yeah, that's great. Now how do you do it? Well, it's kind of a weird thing here. We kind of still put the carriage in front of the horse on this one. G big M small m over R. They put a negative number right here. They said that's the potential energy of one object, small m, in relation to, that's the potential energy of one object, small m, in relation to a big object, big M, when the small object is R units away from the center of mass. When the center of mass of the small object is R units away from the center of mass of the big object. Why on earth did they put negative? I already said it kind of earlier. There's an arbitrary thing that goes on here, guys. It's very arbitrary. It's very arbitrary to you can be kind of arbitrary doing a lot of stuff. Now, why that negative kind of? I'll tell you what I'm going to do. In this logic, for lack of a better way to say it, in this logic right here, if R goes to a very, very, very big number, what is this G big M small m divided by a very, very, very big number? It's something close to 0. If you want to make the distance between the two very, 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 very big, if the distance between the two is very big, R is a very, very big number, this constant divided by a huge number is close to 0. It's a non-zero number, but it's a negative non-zero number. It might be negative 1 billionth, negative 1 trillionth, negative 1,000th. It's a little bit bigger. Notice negative 1,000th is a bigger number than negative 1 millionth. If I am in total debt of $1,000 and my friend is in total debt of $1 million, I have more money than he does. I'm richer than he is. We're both broke, but negative 1,000 is negative 1,000. I owe $1,000. Negative 1,000 is richer than him owing $1 million. That's negative 1 million. He has negative. He doesn't have money. He owes $1 million. I don't have money. I owe 1,000. Negative 1,000 is bigger than negative 1 million. How much richer am I than him? Well, I've got negative 1,000. He's got negative 1 million. Subtract, surprisingly, I'm actually richer by $990,000. Here, notice that the two negatives gave me a positive. Just like this gave you a positive eventually. This is kind of what's going on here. They're making the claim for any large mass, capital M, the greatest potential energy that you could ever have between mass big M and mass small m, the biggest potential energy that you could ever have, is if they were infinitely far apart or close to infinitely far apart. In which case, huge number divided into here goes to 0 in the limit. 0 is the biggest potential energy you could have. All other potential energies are in the negative realm. But when you do subtraction, ladies and gentlemen, it's a wacky bookkeeping method. It's probably the best bookkeeping method there is for this, or one of the best at least, though it is confusing. Well, okay, that's the potential energy between them. So what are you talking about here? How did they get that answer? Why don't you let's take the final minus the initial. Here's this guy, minus a minus here goes. It's my friend and I, right? Me at negative 1,000, my friend at negative 1,000,000. That's there. Minus a minus is plus. Minus a minus is plus. The minus there stays. The other guy minus stays. So here it is. Ladies and gentlemen, that is where they're getting that. They got it from here. Yeah, and you can keep asking the question, how the heck is that? Well, I told you they made it up. They made it up. They made it up, yes and no. Let's go to page 222 and we'll kind of talk about it. They're trying to kind of figure out how you want to say something like this. So they're saying, let me say something. Let me make, so you saw what I did here, and I don't want to erase too much of this because I think it's going to help us if we leave it. But some of this, so you saw where this went. You at least saw where it went right here. On page 222 of the Katz book, they're saying this. Let's consider the whole way we want to look at this thing. The gravitational force of the Earth, for example, on a spacecraft is given by Newton's law of universal gravitation, G/mm over r squared. They put a negative on there because they're attracted to one another. You can rewrite equation in terms of its radial axis. So you can say they don't give. They don't. It's hard to call this one. They don't give a very good explanation how they're using some of the negative here, or at least in my judgment, they're not. Perhaps I'm the one who's off on this one. So let's work with it. Let me kind of talk you through this. They're saying Fg associated with gravity, and maybe that would have been easier. The small g here is fine. I don't think anybody's going to throw a fit, guys. Put a big G there. I don't know, whatever. That's the semantics of it is not the big deal. The big deal is this. Fg is force of gravity, as we say. It goes in the radial direction. I don't want to beat this thing up too badly, but it is a vector, so we should have it there. So the r hat vector, and that's the r's that we had over there, way over there to the far left, you guys. Over r squared. Okay, so that right there is this. It's basically just FR. I don't want to write more than that. I mean, the book has it. You can look at the book on that too. I don't want to say too much more than that. I want to write it like this. Forgive me. And they put a negative here. This idea of a negative is sort of arbitrary and sort of not arbitrary. Sort of very important, and if you play it right, you can get away without using negative symbols. You've seen me do it in the past. You got to be careful. In the strictest sense, given the game plan that they've developed in physics and the bookkeeping, it does have significance. But like I said, you can get around negative symbols. You've seen me do it in the past. Just be careful. Why are they putting a negative in front of it to begin with? We're all used to seeing what Newton said without a negative, and this right here. G capital M small m over r squared equals the force of gravity. And then there's no vector on top. Okay. Because they are attracted toward one another. It is moving inward. It's not, gravity doesn't push something away, it draws toward one another. They draw toward one another. And that's where the negative comes in. They say a lot of stuff. The way the book says it is okay. It's not only okay, it's right, but let me kind of get around it a little bit. They're kind of saying this. They're saying delta U, and this is actually a true story. Let me talk about it, and then let me talk about it, and then let me sort of throw it out the window, not completely out the window, I guess you could say, at least for our gut feeling on this. Delta U, change in potential energy, they keep the negative, guys, and they go RI, RF, FR, dr. The FR is, I said I wasn't going to do that, now I'm doing it. F sub r hat. They're saying FR r hat like that. Okay, that's just a unit vector. That's a lot like the I hat. These are like the I hat, the J hat, the K hat. They're 1 unit long in the R direction. In the R direction, that way, going upward, 1 unit long R vector. Well, I mean, this is important. This is interesting. What is going on? What the heck did that negative mean? We know that FR is a negative, so negative of negative is positive. And from there, we can kind of look at where we're going to go with this thing. They basically, I don't know how to say this. I'm not a spokesman. I'm not a spokesman for Newton and Einstein and everybody else, but I'm very confident they set it up so that it comes out the way we want it to come out, so that we're getting this difference that we talked about. So we're getting, well, I erased the other thing, but you saw me kind of do the game we were playing, guys, how we actually got this thing to be the case, and actually we made it be a positive number. For this thing to be an increase in potential energy, a positive number, the potential energy function has to be negative G capital M small m over R. It has to be negative capital G capital M small m over R. Has to have the negative symbol. This quantity right here has to have the negative symbol in front of it for the difference in the two functions, for the difference in the two values to come out to be positive. It has to be a negative. So if it has to be a negative, they write it down like this, assuming you're going to write this down like this. Well, I'm going to this is true. What they're saying here is true. There's no two ways about it. Let's see what they're trying to say here. See what they're trying to say. What they're trying to say is you got delta U. Let's say this is a big number and that's a small number, and then we'll see what happens. Well, that's important. And we can kind of talk about it. Now, this might be a small number. This might be the smaller of the two numbers. And this might be the bigger of the two. Or this might be the bigger, and this might be the smaller of the two, and that might be the bigger. Let's see where it goes. In this case, we're going to say that's where it started, and it went to a big, small place, went to a big place. We'll just say that for now, to kind of visualize it. If that's the case, you guys, we're going to say it's negative let me not put that on there. Negative, that right there, and that's this, dr. Ri, they made it, ladies and gentlemen, they constructed it so it works. You're going to see that in a second. Let's talk. You might want to say to me, Malus, what's the big deal? Negative of a negative is positive. You might ask me, Malus, what's going on here? Negative of a negative is positive. Why didn't they just write this thing right off the bat and see how the game plays out? I frequently, when I've taught it, I've kind of gone right to here and then gone for it. These are constants for a given circumstance. These are constants for a given circumstance. So you've got what is that? I'll tell you what it is. It's G M. Let's see how I want to write this, guys. Give myself a little bit more room. It's easy to see when somebody writes very large, but the person writing very large doesn't have a lot of room then at that point. But you guys, I need you to see what I'm doing at least. So, okay, we got to here. The integral dr over r squared, the integral of dr over r squared is the integral of r to the negative 2, is equal to negative 1 r to the negative 1. It's equal to negative 1 over r. The integral dr over r squared is negative 1 over r. If you took this and got its derivative, you get 1. Take the derivative of this thing with respect to r, you get 1 r to the negative 2. That's 1 over r to the 2. So that works. Here's our f, ladies and gentlemen. Here's our I. What we have here is, well, let's evaluate it. It's negative. Well, first of all, time out. Put that negative right here. Put the r right here. Negative G big M small m over r. Negative G big M small m over r. Yeah, that's what we said. That's where they got it. That's where they got it. Evaluate between RF and RI. This is negative. This will become negative GMM over RF minus a negative GMM over RI. We've been there. Becomes negative GMM over RF minus a negative GMM over RI. Minus a minus. Minus a minus. You know what happens. Look familiar? That's where we started. That's where we started. Not thrilled by the way this stuff, I mean, they're kind of caught between a rock and a hard place. They're caught between a rock and a hard place. But for the mathematics to work out, for the mathematics to be convenient, they've got to manipulate the signs a little bit. And as long as they're consistent, it's okay. I believe that the number 0 is the biggest number when all other numbers are negative. Sure. If they are infinitely far apart or close to infinitely far apart, if they are almost infinitely far apart, if you allow me to say that, then this number is about 0. All other numbers are negative. They're smaller than 0. 0 is the biggest one. That's all right. Their logic's fine. Their logic works. And this is what we have here. And again, the book goes into it. Look at the book. I mean, make sure you're looking at the book as well when we're doing this stuff, guys. They get into the conservation of mechanical energy. They get into they offer a proof in the book as well that's really nice regarding kinetic energy. It's looking good, guys. Looks real good. Some other stuff that gets said, talk about total energy of a system. Again, this idea of the negative is a matter of bookkeeping. And they kind of go into it. I'm not going to greatly emphasize beyond some of what I just said, but a good page to look at, pages 235, 236. They get into the same idea of what I was just talking about, guys. They're saying, let us start with a circular orbit of particle, a comet or something like that. And they're going to show that they end up getting an answer for the mechanical energy being a negative number. What the heck does a negative number mean? It means it's a number. It means if I get a difference between two numbers, just like my friend being in debt $1 million and me being in debt just $1,000, I'm richer than my friend by $990,000, 990,000 joules. Negative 1,000 joules compared to negative 1,000 joules compared to negative 1 million joules. How much more? Not how many times more. Let's not go for a ratio here. You got to go with subtraction here. What's negative 1,000 minus negative 1 million? That's positive 990,000. They kind of go into that argument on page 235. You might want to look at it. I'm not going to greatly emphasize that, but it's still a good problem. You might want to look at it. I think that's about it. I mean, there's good stuff in here, guys. There's more stuff in the book than I'm going to have time to that any teacher has time to say in any lecture, whether he's right in front of you or not in front of you, trying to do the filming that I'm doing here. Look at it, try to look at the main stuff, and try to look at the stuff I've also written, even the stuff I've done in Canvas. I wish I could do every single one of those problems live, either in person or on film. Even those problems that I've worked out, they're very hard to do live. I can only do a fraction of them. You've seen how long this stuff takes. But you're going to do your work, you're going to work hard, and you're going to do this right, okay? The next video I will discuss those problems in Chapter 8, right there. All right, guys, thank you for your time.